In Unit 5, we focused on exponents and radicals. So with our review, we're going to start with the properties of exponents. The zero property says that anything to the power of 0 will equal 1. The negative property says that you need to use a reciprocal or a fraction, moving that negative power into the denominator with its base. When you move it, make sure the power becomes positive. If you have the same bases being multiplied together, keep the base, but you will actually end up adding those powers. So whatever two numbers you have, you'd add them together. If the same base is being divided, you need to subtract those bases, or those powers. And then finally, our power of a power property, you have two different bases, x and y, each with their own power. For each of their powers, so for x we have m, you multiply it by the power outside of the parentheses. So for y, you multiply the power n times the power p. So let's start applying these properties to different expressions in order to simplify them. For number 2, we have 3 is multiplied by x to the 0, but that just means it's 3 times 1. And then you still have y cubed. So just to make it look a little nicer, 3 times 1 is 3, keep the y cubed. For number 3, we have a product going on, things are being multiplied, so if bases are the same, we're going to add their powers. So let's see, we have x's on both sides of the multiply problem, so we would take 3 and we're going to add it to the negative 8. That would give us negative 5. We have y's, so their powers can be added up. Notice that this y is a 1, we're going to add it to this y that has 4, giving us 5 altogether. And then if you have numbers that are bases, go ahead and multiply them. So 4 times 2 is 8, and we'll always leave our values up front as coefficients. This actually also includes the negative property. We don't want to leave negative powers in our answers. So I'm going to keep 8 and y to the 5th where they're at because they already have positive powers, but I'm going to bring x to the denominator with a positive power of 5. And that would be your answer for number 3. For number 4, we have our 2 base, 2 times 4 is 8. And we have the same x base, one with a power of 7/4, the other one has a power of 1. If we want to be able to add these values, you need a common denominator. So recognize that 1 is really just divided by 1, so we can get a common denominator of 4 if we multiply this power by 4 in the numerator and denominator. So the new power is 4 over 4. We're going to add the numerators, 7 plus 4 is 11, but we're going to keep that common denominator of 4. For number 5, we're going to employ that power of a power property because we have a lot of bases inside parentheses raised to a power outside. So first we have 2 is a base with a power of 1. And if we multiply that base power 1 times 3, we have 3 altogether. For the base a, we have negative 2 times the outside 3 to give us negative 6. And b is negative 3 times 3, negative 9. So remember, you're just distributing each power to the outside or multiplying. Now we can simplify. We have 2 to the 3rd is 8, and that's a positive power, so it's just going to remain. Anything with a negative power is going to move to the denominator. So a will move down with a positive 6, and b moves down with a positive 9. For number 6, it's very similar. You have a power to multiply to the fraction. Just one power. So your base n would take 3 over 1 times 10 over 7. Remember, you only multiply the numerators, so 3 times 10. And then you multiply the denominators, 1 times 7. So if you don't have a fraction, make sure to put it over 1. And then when you multiply across numerators, multiply across denominators. For 7 and 8, we're working on the quotient property. First, we try to figure out, could we really even divide 4 by 3? And you can't without getting a decimal. So the 4 divided by 3 is going to stay. There are no x's in the numerator, so we're just going to have to leave the x in the denominator as is. However, there are 4 y's in the numerator and 2 in the denominator. So we always leave our variable in the top until we find out if there's a negative. So take 4 minus 2, the numerator's exponent minus that of the denominator, and 4 minus 2 gives you back 2. So there's no reason to move the y because it has a positive power. For number 8, again, check the numerical bases. 2 does not divide by 3, so those are going to remain. For the x's and the y's, we'll have to employ our subtracting rules since they're being divided. So for x, we have 2 over 1 is the numerator, the exponent in the numerator, but 1 over 4 is the exponent in the denominator. So if I want to subtract these, I need my common denominator of 4, which means both numerator and denominator get multiplied by 4. You can do all this on your calculator if you need to help you out. So we're going to take the numerator 8 minus the numerator 1, giving us 7. Remember, this is from x, with the common denominator of 4. For the y's, we have y to the 1 minus 1/2, and 1 minus 1/2 is just 1/2. So there are no variables remaining in the denominator, just the base of 3. So that takes care of both targets 5.1 and 5.2 using your properties with both integer and rational exponents. So 5.3 is where we want to convert between having a fraction as an exponent and a square root or a cube root, some sort of radical. So when you know you start with the fraction in your exponent, you want to convert to a radical by moving the denominator out to what we call the index of the radical. And then the rest of the expression, 15x, goes inside with its numerator power of 1. If you start with the radical, you have to undo it. Remember, if it's a square root, that index is a 2. So we're going to use the 3k as the expression with that numerator value of 3 and bring the index value of 2 to the denominator. And that's converting between rational exponents and radicals. If you want to simplify a radical, or even perform operations and then simplify, you have to know your perfect squares list. So we have 1, 4, 9, 16, 25. So that's 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, 7 squared, 8 squared, 9 squared, 10 squared, and you could keep this list going. So I'm just going to hang these out to the side. We're going to need those when we want to break down a square root. So if you need to simplify an expression by multiplying two radicals, just make sure they're both square root values to make one big square root, and multiply the inside radicands together. 12 times 2 is 24. And then here's where the simplifying step comes in. If you want to break down the square root of 24, find a perfect square, 4, that goes into it. So we're going to rewrite the radical using the perfect square of 4, and if you divide 24 by 4, you would have a square root of 6 left over. Since 4 is a perfect square, its root is 2, and then 6 remains in the square root because it's not a perfect square. If you have a multiplication problem where there's coefficients, put those together by multiplying, so 3 times 2, and then just like number 11, we're going to multiply the radicands 10 times 4 to get 40. And now that we have one radical, we're going to try to split it into a perfect square. So for 40, again, it just so happens that it divides by the perfect square 4, and that would be times 10. So we kind of didn't even want to undo these radicals, but that's okay. So the square root of 4 is 2, and 6 was being multiplied by square root of 4, so we're going to be able to multiply 6 by 2, and leaving the square root of 10. So your final answer here would be 12 square root of 10. Adding and subtracting have a little bit of a different rule. If you want to be able to add or subtract radicals, they have to be the exact same radicand. So if you look at number 13, we have the square root of 3 is in both of the first terms. The radicand stays the same, kind of like when you're adding and subtracting fractions with their denominator staying the same. So keep square root of 3, but add negative 3 plus 2 from the coefficients. So one more time, this negative 3 got added to 2, giving me negative 1. but 3 square root of 2 cannot be added with it truly because it has a different radical. So it just remains at the end of the expression. So for 14, what you would want to do, since none of the radicals match, you try to break down what you can. So 12 divides again by our perfect square of 4. And if you divide 12 by 4, you get 3. So for the first term, 3 square root of 12, we rewrite it with square root of 4, square root of 3. The middle term, negative square root of 3, cannot be broken down. And then for 45, you can divide that by a perfect square of 9. And if you divide by 9, you get 5. Square root of 4 is 2, so we're going to replace that term. And there's nothing we can do about the square roots of 3. Square root of 9 is 3, so we're going to bring a 3 out. And nothing we can do to simplify square root of 5. Multiply your coefficients that are with the same radical. And then you should realize you have 2 of the same radical, square root of 3. So keep the radical, but combine the coefficients. 6 minus 1 is 5. And then 9 square root of 5 is just going to have to stay the same. Those 2 final terms cannot be put together because their radicals don't match. So for the 3.0 A and B, you have just a little more intense problems where you have more properties going on, more variables involved, and then just a mix of multiplying, adding, and subtracting. So I'm going to work these out, and you'll be able to view the steps as you'd like. Just make sure you pause the video as you look it over. So again, feel free to pause here and work out the problem your own and kind of check in with what you see on the screen. There's some explanations from step by step. The answers are in the dark blue. And then you can do the same thing, pause, and work on 19 through 22, then come back and check the work.